So I want to talk about a collision, and we're going to use the conservation of momentum, this physics law. We're going to use it plus a judgment call based on the collision type in order to make a prediction. So honestly, this is kind of the classic introductory momentum conservation problem that you would find in a homework or on a test, for example, in early years college physics or um, even the last 2 years of high school. So the setup looks like this. I've got, in this particular case, I've got this object. It's a 2 kilogram mass. I'm calling it number one, and it's headed towards the right with 2 meters per second of motion. So you can calculate very easily the momentum of this object number one. And here is a 3 kilogram object headed towards the left at 1 meter per second. I just made these values up. If you felt like it, you could make this 35,000 kilograms and this a tenth of a nano kilogram or some whatever you want. And then this could be some really fast speed and this could be some really slow speed. It doesn't even matter. But these numbers are easy to calculate in my head, so I'm going to use those just to try to understand what's going on. In this situation, these two things are going to run into each other and have some sort of a collision. So what happens during and after the collision is up to the collision type. We're going to start with inelastic first as a collision type, and then we'll go and study what would be different for the elastic case. These are both ideal types of collisions. Yeah. So here is what I might call initial. So this is pre-collision. Even a little bit of time later, they still haven't gotten in contact with each other. So it's pre-collision until actually the collision finally begins to start. And then that collision, depending on the collision type, takes a certain amount of time. And then the outcome of the collision, like after a long, long time, still depends on the collision type. But nonetheless, this is the initial state or something like that. Okay. Let's see. Some other things that we should say is we'll say that this is horizontal, and what I mean by that is gravity won't change anything, or gravity is just not important, because if there's a weight force, there's also a normal force for each of these objects. So gravity is not interesting in this horizontal world. And also, no friction. So you could say that maybe this horizontal surface is some ice, for example. So no friction and horizontal. All right. This comes up later on how we use the conservation of momentum. Yeah, so let's continue. Let's say that collision type, so if collision type is perfectly inelastic, so I forgot to include this, but this is a particular case of inelastic collision type. So if the collision type is perfectly inelastic, how do the two objects move after their collision is finished? So how do the two objects move after the collision is finished? What you're looking to do is give the velocity of number one after the collision, or final, and also velocity of number 2 final. So this is the goal. So let's go do this. So I'm going to use the conservation of momentum. And the conservation of momentum in this particular case is that the total momentum before the collision, so I'll put P total initial, is equal to the total momentum after the collision. And the reason is no external forces. So this is not actually true, so I'm going to erase the S and put no external net force. It's what I'm referring to is the fact that gravity and the normal force net up to 0 in the up-down direction. And because I'm also, yes, and then also there is no friction in the sideways direction. So after the two objects are given their initial momentums, nobody needs to continue to push on them for them to continue moving at each other. So nobody's pushing on the two objects. The only thing that number 2 is ever going to encounter is, or the 2 kilogram object is only ever going to really encounter the 3 kilogram object in order to have its momentum changed, and then also the vice versa for the 3 kilogram object. So no external net force. This is why we can invoke this particular version of the conservation of momentum. Anyhow, I'm going to move on. I just want you to see the flow of solving a problem. So P total initial equals P total final. So P total initial, I can actually write it down, but let's unfold this. So P total initial is P1 initial plus P2 initial. And P total final is P1 final plus P2 final. P1 initial is 2 kilograms times 2 meters per second. That's P1 initial. That's the initial state, pre-collision. And then P2 initial, we have to be really careful. It is 3 kilograms times the speed of 1 meters per second, but you can see the opposite directions of the momentum, so there must be a relative minus sign. I'm going to give the minus sign to the leftward motion, and the rightward motion is going to take the plus sign. So this will be 3 kilograms times the 1 meter per second there. So 3 kilograms and 1 meter per second multiplied. So that's all that stuff. Let me move this equal sign down so it looks a little clearer. And then these things, so I don't know V1 final or V2 final. I don't know their values. That's actually the goal of the problem. So I'm just going to put them in as symbols. So P1 final is the mass of number 1 times V1 final, like that. And then I'm going to put in plus 3 kilograms times V2 final. There's a chance that when these two things have their collision, after the collision, the two objects could be headed both towards the right. We should have plus and plus on the velocities. Or maybe they're headed both towards the left, in which case the velocities would both end up being minus signs. Or maybe the 3 kilogram goes towards the right and the 2 kilogram goes towards the left. So the V2 final would be positive in that case, and V1 final would be negative in that case, right? So, but lots of things can happen, but we have just, so this equal sign is because of conservation of momentum. And if I look at this, this is one equation with two unknowns. So at this point, you should remember from algebra that this is not solvable unless there is more information. And the more information is actually the fact that we are in a perfectly inelastic collision. So momentum conservation, strictly speaking, doesn't actually finish our problem for us. It sort of sets the stage of the problem, but in fact actually it gives us, it turns out, one equation that has two unknowns in it. So in order to say more, we have to know something about our collision. The collision type is perfectly inelastic. What perfectly inelastic implies is that the final state of these two objects is that they are stuck to each other. We had a 2 kilogram object and a 3 kilogram object, right? And inelastic, so perfectly inelastic means moves together after collision.